Swayam Prabha. Digital India. Educated India.
Welcome friends, welcome to the today's class on linear combinations. As you know that GPS observables are fraught with errors, and to improve the accuracy in GPS positioning we need to improve the quality of the GPS observables. That means we want to reduce the errors associated with the GPS observables. In the last class we have seen that the errors associated with GPS observables can be minimized or reduced by going linear difference methods. Today in that linear differences method or method of differences, we do take the difference of different same observables from different satellites or from different receivers. Now today we will discuss another type of combinations of GPS observables, which is called linear combinations, in which we will take the combination of GPS observables of different types, but they will be from same satellites. As you know, GPS signal contains observables of different types like carrier phase observables as well as code pseudo range observables. So in any GPS signal nowadays we get 3 types of carrier phase observables and 5 types of pseudo range code observables. So these observables may be combined in such a way so that we can minimize the different types of errors associated with the independent observables. So in order to carry out these linear combinations, we do take the differences, undifference observables or double difference observables, as we have found in the last class. Now today's class regarding combinations or linear combinations of GPS observables, we will talk on introduction and then different types of linear combinations. I will take 3 carrier phase linear combinations, then Melbourne-Ubena linear combinations and some dual carrier phase linear combinations. Now as I told you that the linear combinations are the observables derived from other observables of different types from the same satellites, and we make use of the undifference observables as well as double difference observables to find out the linear combinations observables. Now in doing that we will effectively change the measurement model from linear or single or original measurements to combined measurements, and in doing that we will eliminate the error, most of the correlated errors, alleviate processing computations as well as reduce bandwidths. Now let us take the 3 carrier phase linear combinations. That means we will make use of the carrier phase observables from a GPS signal of L1, L2 and L5 carrier phases, which are, we can represent it by these are the 3 carrier phases that is available from a GPS signal. Now if we combine together these 3, then suppose we get a carrier signal of linear combination type having phase phi LC, so that can be represented by A into phi L1 plus B phi L2 plus C phi L5, which may be represented mathematically like so. This is the phase of the combined signal, and these A, B, C are the different coefficients which we will learn afterwards more. So, by multiplying these different, we can arrive at some characteristic phase of our desired nature. Now, if next the frequency of the combined signal will be, as we know that the frequency is the time rate of change of phase. So, if we take the frequency of the linear combined signal will be like this, which is also we can write like so. The frequency of the combined signal will be the multiplication by the parameters A, B, C of the corresponding frequency of the signal. Now, the wavelength of the combined signal, as we know, wavelength is equal to C by F, that means the wavelength of the combined signal will be equal to this. Now, through algebraic manipulation we can get it. Now, frequency of this is equal to A into FL1 plus C into FL5. So, our will be equal to, we can write it like this, C now you know this C is defined from, this is the constant C and this is the velocity of the light. So, that distinction is to be done. Now, from this we get A into lambda L2 lambda L5 plus B into lambda L1 lambda L5 plus C into lambda L1 lambda L2, and we will get lambda L1 lambda L2 lambda L5. So, this is what is the wavelength of the combined signal. And next our what will be the integer ambiguity of the combined signal. Now, we know integer ambiguity is nothing but phase by lambda. So, integer ambiguity of the combined signal will be equal to phase of the combined signal divided by the wavelength of the combined signal. Now, we know the phase of the combined signal is summation of the individual signal multiplied by the constants. Divided by lambda LC. So, if we now we have to make some algebraic manipulation. So, for this I can write this thing by algebraic manipulation. Similarly, B into phi L2 lambda L2 plus C into so this is what we can get from here. Now you can see this is a constant because this is the wavelength of the L1 signal, this is the wavelength of the linearly combined signal, and A is also constant. So altogether this is a constant, say it is I, and here this factor is nothing but it is the integer ambiguity of the signal L1. So phi by L1, so integer ambiguity of the L1 signal. Similarly this is another constant J suppose, and this is the integer ambiguity of the L2 signal, and this is again a constant K, the integer ambiguity of the L5 signal. So we see that the integer ambiguity of the combined signal is a summation of integer ambiguity of the individual signal multiplied by some constants. These constants are again depend upon the wavelength of the signal as well as wavelength of the combined signal and a factor A. So in this way we can find out, we can get the different characteristics of the combined signal which really provides us an insight into the nature of the combined signal. And finally, as we are mostly interested in the errors that will be propagated out of the combination, so if we consider ionospheric error and tropospheric error as well as noise and multipath are the primary sources of errors in observables, let us say what will be the error propagated. So the amount of error that will be propagated to the combined signal, that is the theory of error propagation, we can write like this. So this is the error, root mean square error of the combined signal due to the ionosphere, troposphere and noise and multipath. So these are the errors, root mean square error of the individual signal L1 signal in the ionospheric error, tropospheric error, this is the noise of multipath error. So our errors will be defined in terms of the errors that is associated with the L1 signal, which is the most prominent signal, and this is multiplied by and this, that means this multiplied by the this will be the amount of ionospheric error in the combined signal, and this multiplied by this, that means this is what is the error in the tropospheric signal, and your so, and this multiplied by this is the error due to noise Now we can see that we can found that the errors associated with the linearly combined signal is the weight, these are the weights, weighted sum of the error that will be associated with the ionospheric error, tropospheric error and noise and multipath. And these weights, you can see these weights are primarily dependent on the coefficients A, B, C and the nominal frequency FL1, FL2, FL5. So these are the prominent thing on which the error will depend, and since the amount of error is the weighted sum of these weights, weighted sum, so these weights are called the amplification factor of errors, because depending upon these weights the error gets amplified or reduced in case of combined signal. Now if we can make this as 0, then our this multiplied by this 0 will be 0, so our ionospheric error will be 0. So the condition for ionospheric error to be reduced to 0 or nullify is to make this 0. Now and to make the tropospheric error, to nullify tropospheric error, we have to make this equal to 0. Similarly, now you can see here all these parameters a square plus b square plus c square. Under all circumstances, whatever we take the value of a, b, c, this summation will be always a positive number. This indicates that the error due to noise or multipath will always increase in case of linear combination. Now as you know that the observables are different in different campaigns, so also the errors that will be associated with the GPS observables. Thus the constants A, B, C we take also will vary from campaign to campaign to arrive at a particular characteristics of the combined signal. Now how to decide the value of ABC? The criteria for deciding the value of ABC is to make this combined error should be minimum, because this is the primary objective of our linear combination, is to remove or minimize the error associated with the linearly combined signal. So we have to make this expression to be minimum, or in some cases because many times we may not make the minimum, so it should be guided that the errors due to ionosphere and troposphere as well as noise should be minimum, should be less in linearly combined signal than that is available in only L1 signal. Actually the amount of error that will be associated with the linearly combined signal will depend upon the baseline length of the GPS observable and the amount of errors that will be associated or the mutual errors. That means what is the errors in ionosphere and troposphere multipath mutually available inside the observables, and as well as it will also depend upon what is the degree of accuracy a user wants to be associated with the observable. So on these factors the quality or the amount of errors that will be available in linearly combined will depend. That means we have to choose the values of A, B, C. With this I would like to go for the next type of linear combination, which is widely prevalent in today's scenario. Nowadays the linear combination known as Melbourne-Urbana linear combination is most widely used for minimizing or for as a preprocessing operation towards GPS processing, to minimize the error associated with the GPS observable. Now Melbourne-Urbana linear combination. Actually, in this linear combination, we make use of the phase observables of both the carrier signal L1, L2 as well as the pseudo range of signal P1 and P2. So, in this case both the carrier phase observable as well as pseudo range observables gets combined, as the objective is to reduce, and as a result of which we do get the observable which are free from errors arises out of ionosphere, troposphere, satellite geometry as well as clocks. Now the wavelength of the Melbourne-Urbana is like this, 1 by FL1 minus FL2, FL1 multiplied by the, I will use the signal symbol L1, that means this is the carrier phase observable range of the signal L1. Plus 1 by FL1 plus 1 by FL2, FL1 pseudo range of the code P1, PR means pseudo range, and FL2 pseudo range P2. So, this is what is the wavelength, and correspondingly another parameters as we have done in the last derivation we can do, and in that way we can get the characteristics. These parameters will provide us to get an insight into the characteristics of the signal, which will help us to see what are the errors and what is the errors has been removed or minimized, and what are the error already present, still present, and accordingly we can make use of this. And apart from this, actually nowadays a plethora, some prominent dual frequency or dual carrier phase combination signals or observables are available, or linear combinations are available. So, dual frequency linear combinations. So, of this there are a big list among these which are most widely prevalent, that is wide lane, then narrow lane, then ionosphere free, and geometry free. These are the linear combinations, dual frequency linear combinations, which are most widely used, and in all these cases it is the L1 and L2 carrier phase observables are being used, and corresponding to our A and B, as we have seen in the 3-phase carrier frequency. In case of wide length it is the 4.53, and for B it is 3.53. So, that means the signal is, we get the phase of the linear combined wide lane, we get 4.53 phase of L1 minus 3.53 phase of L2. Now we know that the frequency of L1 is far greater than L2. So, the frequency of the linear combined that means wide lane linear combination will be more than what it is available for L1 or L2. So, when the frequency is more means ionospheric error will be reduced. So, we can reduce the ionospheric error further in wide lane. The cycle slip can be detected, restricted, and integer ambiguity can be resolved easily, but this is having a high noise. So, noise is a impediments, and as a result you see that the errors are very big, 5.76 meter. So, now in case of narrow lane we make use of A is equal to 0.56, B equal to 0.44. So, here use so you can see the linear combination narrow lane, ultimately because L1 frequency is more, L2 frequency is less. So, ultimately we will see that the combined frequency will be less than, frequency of this will be less than the frequency of L1 single. So, frequency is less means your ionospheric error will be more, but less noise. So, if we want to create a signal which will be having less noise, then we should make use of narrow lane concept, and this constants we may use. Then ionosphere free linear combination, where two so this is the constants which we have to multiply with the phase of the L1 signal and phase of the L2 signals, and again we will find out, we will get frequency of ionosphere free will be more than the frequency of L1 signal, which will provide us a good signal for getting the ionosphere free. We will be able to compute the ionospheric error easily and we can make it free, and this type of signal we design for baselines which are very long, and geometry free, where we get the signals having constant multiplied by 1 and minus 1. So, here also we will get a frequency less than the frequency of the L1, and this will provide us a geometry free signal, but it will have so many other errors. So, depending upon the purpose what for we are looking for, we want to pre-process the signal, we can go for different types of linear combinations, and we can reduce some of the parameters, we can enhance some of the parameters. With this I want to conclude today's class, but before that I want to summarize today's class. Derived observable can also be obtained from different types of observable that is available within a GPS signal. We make use of different carrier phase observables and the code phase pseudo ranges available in the GPS signal arriving from the same satellite. So, this is the condition we should take into consideration. In linear combination we make use of signals from the same satellite, that helps in removing or minimizing the correlated errors. Then as the errors in GPS observable depends on the nature of campaign and vary from campaign to campaign, so also the constants that will multiply to get the linear combinations also vary. However, to make it optimal we should see that the combined errors in the combined signal should be less than what is available in a single L1 signal, and the optimal value of the constant ABC will depend upon the baseline length, the amount of different types of error and their mutual dependence in the observables and the amount of accuracy we do look for our combined signal. One of the most widely used linear combination is the Melbourne-Ubena, which is very good in removing or minimizing the ionospheric error, tropospheric error and other geometric errors. And there are some other dual frequency linear combinations are available like wide lane, narrow lane, aerosphere free, geometry free, etc., which has their own characteristics, and depending upon the need we can make use of these different types of linear combination to serve our purpose particularly. With this I like to conclude. Thank you and see you again in the next class, which will be on GPS processing. We will be talking on GPS processing in the next class. Thank you.